Okay, so there is a chapter of a book I published for Cambridge University Press, whose title is Naive Model Theory. And Erdan has this chapter. And
you can find also in file in Teams now.
Okay, Ivan already placed in the file in Teams. You should read it in parallel, because I am the last part of the lecture I gave last time, the main part of that lecture, in fact, is taken from that chapter. So I advise you to try to read it while I'm including parts of that chapter along the the lecture. And if you have any doubt, you can talk with Erden. So we are sure that Erden would read this chapter, because it's part of his duties to read this chapter. I think it is very important when you are doing research to understand what you are doing. Before we proceed, I want to explain you better why I told you in the last lecture so many philosophical ideas. If on the right side you have the real world, and here you have the mathematical objects. Okay. If you have a body, let me draw the beam following the style of Galileo. So you have this piece of Galileo was in the picture of Galileo, there was a piece of wood with a big stone. So this is an object. This is an object in real world. Okay. Then you take a body having a volume, a subset of R3, having geometrically some dimensions. So you invent the mathematical model for the volume occupied by the body. And you call it C star, which is, we said, a subset of R3. Okay? So that you have a set of triples of real numbers. You have called it C star. Okay. Now, who is telling you that this is a body? Nobody. This is a mathematical object. Okay. So C star is a mathematical object, and it is mimicking, describing the volume occupied by the body. Okay, remark that I am, maybe we should call it beam, by the body beam. So we invent, I told you several times that human beings don't understand differences between different concepts if they don't use different names. In order to specify in our reasoning that the physical object is an entity, and C star is another entity, it is very useful to use different names. So let's call beam the object and C star the model for a particular set of properties of the object. So C star models the shape of the beam. Or in general of the considered body. Okay, because could be even a more complicated body. Then we will, in the real world here, we have that the body changes its shape because of the weight we have applied. My drawing is very bad, but you understand what I mean. Okay. And then the function defined in C star having values in the Euclidean three-dimensional space of positions, this key gives you the mathematical model for change of shape. Okay, of the body. Then we have that a body having this original shape has this other shape after deformation. So, for instance, you have a compression. So we need to describe deformation. So a model, a mathematical model for deformation. Here, things become rather difficult. Why? Because absence of deformation means rigid body. Remark that I'm writing on the left column. A rigid body is a mathematical entity. You know, you read in the books very often statements like, there is nothing like a rigid body in reality. Actually, this is a rather empty statement. Rigid body is a map, if you like. Instead of rigid body, we should say better a rigid placement. A rigid placement is a placement which is preserving the distances. And we have seen that a placement preserves distances if and only if it has this structure where Q is inside ORT. Q in to Q transposed. So we describe the absence of deformation with a formula. And then we understood that if this is your body in the real world, you must take a small piece of the body, a piece of the body which is small enough and you must consider grad key, which we called F, as a linear map, and this grad key tells you what happens around the small part of the body on which you focused your attention, and F transposed F, which we have called C, measures locally the deformation. Okay, so what we are doing, we are inventing a I close the region where real world is described. Okay, we are inventing a mathematical model where, under some assumptions, some bodies and some of their deformations are described. Okay? So you should never confuse the mathematical model with the reality. This is very to confuse reality with the mathematical model is very dangerous. Why? And I give you an example from the history of physics. Then we start the technical part of the lecture of today. I told you that Greeks were modeling the planetary system with the Aristarchus model. So they assume that there is a sun and in the center, and that every planet, including the Earth, Mercury is inside, Saturn is outside, Jupiter. So there are these planets, and they invented a geometrical model. And in this geometrical model, each planet was a point, and each planet was moving with a certain period in a circle. Okay. Then, by the way, Greeks knew that this was a mathematical model whose range of applicability was limited. Okay. It seems that Seleucus, a scientist living probably in a part of modern Iran, did invent the theory of tides, describing the interaction between the sun, the moon, and the water constituting the ocean. So it is clear that Greeks, we say Greek, it doesn't mean Greek with genes from the Greek people. With Greeks, we mean those who were speaking in Greek while writing books, scientific books. Okay, so in a sense, they could say that I am English, following this definition, because I wrote everything in English, even if I never gave up my Latin style construction of sentences. Okay, so Seleucus knew about the difference between the physical object Earth, the physical object Moon, and the model used for describing the motion of the Moon and the Earth. He was, in fact, capable to invent another model where the Earth was a big ball and the ocean was a layer of water around the glued around this wall, and the moon and the sun were attracting the water in the tides. You know, I discovered with surprise that many students do not know the origin of tides. There is a mathematical model which is rather sophisticated, which tells you how there is a dual period of the tides. And the reason of this dual period is that the moon and the sun, even if they are very distant one from the other, the moon is closer to the earth, the sun is very far. However, the sun is heavier than the moon, so that their influence on the motion of water is comparable. Okay. Now, why I'm telling you this? Because even if Greeks knew that a model is a model and it is not the real object, during Middle Age, okay, they started talking about metallic, or I don't know which kind of rails, which were existing objects. They started speaking about the spheres where planets were hammered on, and stars, the sphere of stars. And they imagined these spheres as moving around the Earth. So they gave a physical essence to the mathematical model. So they confused the mathematical model with the reality. And this is very bad. Why this is very bad? Because one mathematical model could be not capable to describe some aspects of reality. We will see that deformation cannot be described always by C. Sometimes you need to introduce other tensor fields for describing the deformation. If you believe that the body is the placement key, and if you believe that the body, the shape of the body in the reference configuration is C star, and if you believe that key of C star is the actual shape, so if you confuse the mathematical object and the physical object, then you cannot change your model anymore. I had a terrible fight at the beginning of my career with many people, simply because I wanted to introduce grad C as a new deformation measure. But people were not ready to accept this because they believed that the body has a deformation which is C. So they believed that I was changing the reality of a beam. Okay, so it is very important that you make the difference between the mathematical model and the physical object. Okay, by the way, we will discuss somehow other possible models for a deformable body. You could introduce, instead of introducing capital X inside system and a placement key from capital X into the set of placements. This is the continuum model. We could also introduce a set of springs and masses. So we could introduce a discrete model for your beam. And sometimes this discrete model is more useful than the continuum model. So at the end, if you confuse the physical object with the mathematical model, you may feel very unhappy when you change the mathematical model for a reason or another. Okay. Okay. However, when you have described the kinematics of your system, so when you have described the configuration set, the configuration set is the mathematical model for state of the physical system. So your physical system, think about the planets, is in a certain state. It means that the moon is somewhere, the earth is somewhere else, Mercury is in another position. Okay. Then in your mathematical model, you have points located in some parts of some circumferences. Okay. We call configuration an element of the space of configurations. And the space of configuration is a mathematical model for the space of states. I want to give you here an example. So take a, I'm sure, I don't know if you were playing with magnetic needles. So take a magnetic needle which is very small, and you have the North Pole and the South Pole of the magnet, of this small magnet. Okay. So you have a physical object, and it has its own state. Okay. Then imagine that you take this small needle and you throw it, and it has a parabola as a trajectory under the effect of weight and friction. So you have friction and weight. Okay. The mathematical model used for this needle will be the model of material particle, and the configuration is given by its position. So if you know the position of the needle at instant t, you know the configuration of the particle of the needle. Okay? Now imagine that you are throwing this needle in a region of space where you have a magnetic field B. So the state of the system is not described in a detailed way if you use only the model material particle. In order to describe what is happening to your needle, you must add the orientation of the vector going from south to north. So you need to give the needle as an orientation or another one, because this orientation gives you important informations about the forces applied to your needle. Okay. So the state of the system needle, magnetic needle, is described in model 1 by the position. In model 2 by the orientation. I'm sure that you have heard the word spin, and the magnetic orientation and the position. So you understand clearly that as you need to distinguish between the physical object and the mathematical model, you need to distinguish between the concept of state of a physical system and the concept of configuration, space of configuration in the framework of a given mathematical model. So the space of configuration is a mathematical entity. A configuration is an object, an element of the space of configuration, and the same physical object can be modeled by different mathematical objects. In particular, different mathematical models may use different spaces of configuration. Spaces of configuration. Okay? Okay, so once you have specified the kinematics, and in our case, the kinematics is specified by the set of placements And these placements, if you remember, need a gradient. The determinant of the gradient of this must be greater than 0. So you have specified your space of configurations. Then you have a problem. You want to forecast the stable equilibrium shapes under specified external interactions. So let us split once more. Here you have the real world. So you have your body. Now I am drawing a potato. Okay. Then you imagine that you have hammered a part of your body here. You take another part of your body there and you place it in another position. So you have what is called an hard device. So you have a system, an hard device, it is capable to impose displacements. Okay? This is an hard device. Erden, if you want to know what is an hard device in some circumstances, ask to Cardillo to show you the machine which we have in the lab in Giuliano. Okay? You will see a system which can impose for small bodies the placement of a part of the boundary of this body. Okay. Now, mathematically speaking, you have C star, the reference configuration, and how do you model the effect of hard device? It is very simple, and this is the reason for which we start from this kind of hard devices. The placement of X is equal to X when X belongs to a part of the boundary of C star, which we call 1. This is the boundary of C star is the surface around C star. Okay. C star 1 is where we impose that no displacement can occur. Okay, so the placement of the material particle X, which belongs to the boundary, the part C1 star of the boundary, is blocked, while you have another part of the boundary, which we call DC star 2, where the placement is equal to a given function u0, the displacement. So the placement is given by the position plus a displacement x0 x belongs to the boundary, to the part of the boundary. So we impose what are called essential boundary conditions. So our space of configurations is the set of key belonging, we start with the class C1, then we'll see that we need something more, but let us follow the idea of, Lagrange. Okay, then we have that the determinant of grad key is greater than 0. Okay, and then we have that key of x is equal x in the boundary of C star 1, and key of x is equal to x plus u0 of x in C star 2. Okay? And we call this space of configuration S1, 0. 1 means that we have the first derivatives, and 0 means that we have blocked the placement in a subset of the boundary. Okay? In order to avoid that this body can have a rigid rotation, which is can cause troubles, because this body should not have rigid rotations if we want to find easily the stable equilibrium. We assume that this is a simplification. We assume that in boundary C star 1, we have three points which are not in the same line. So we have blocked three points. Okay. Okay. Now, the general principle of minimum of energy can be finally postulated. Why? Because it tells a general formulation of it is the following. Given the set of admissible configurations, in our case, the set of admissible configurations are those configurations where key capital X is X in the first part of the boundary, and key capital X is X plus U0 of X in the other part of the boundary. Okay? Of course, it is differentiable. I mean, you specify the properties you mathematical properties which you are accepting for the configurations. The stable equilibrium is attained when the total energy functional is minimum. This is still vague enough, but consider that this statement is so vague that you can apply it to every mathematical model where you have specified the set of admissible configurations. So in a sense, this principle of minimum of energy gives you a meta theory. It gives you how you must invent new theories. Let us try to, the flow chart has to be the following. First, these ideas were formalized in modern times by French people. So let us say in French, la cinématique d'abord. First, start with kinematics. So the first move when you build a theory, you must invent 1.1, the space of configuration, 1.2, motions. Okay. In the particular case, we invented T of X and T. Okay, so we started specifying our kinematic. Then, second, define an energy functional in the space of configuration. Yes, in the space of configuration. 3, define admissible configurations. Finally, find the minima of energy functionals. This will solve the problem of equilibrium. Okay, then there is another step for dynamics we will discuss later. Okay, this will require the definition of action functional. Okay, but this point 5 we will discuss later. So this scheme has been used for relativity, for quantum mechanics, for generalized continua, this is what we read in available books. I mean, not lost. However, some experts in Greek science declare that a version of this scheme was used also for the theory of solar system and for the theory of machines. Why it is not clear, and you need experts in Greek science for doing this statement? Because Greek books have been lost, or those who were copied were corrupted. Imagine that some books by Archimedes arrived to us via the translation from Greek into Arab, and from Arab into Latin. Other books were translated in Persian, and then translated into Latin, and then into English. There are many ideas which were deformed in the translation. Okay, and so the confusion of mathematical model with physical objects started because of these translations and so on. So I think it's important to study the origins of the theory of the solar system, the theory of the machines. By the way, I have found a book where they claim that also fluids, the theory of fluids, was studied by Archimedes. By the way, he studied the floating bodies. He studied the equilibrium of floating bodies and the stability of vertical equilibrium of floating bodies. This is sure, we know this. So at the end of the story, we are nearly sure that the theory have been invented. Just a second. Sorry, I needed to say something to my mother. Okay. So the theory developed by Greeks is not important, as somebody said, because I have a Greek origin and I want to prove that everything has been done by Greeks. The true, I have a Greek origin because South Italians are members of Magna Graecia. What I want to underline here now is that every known theory has been formulated at first by the principle of minimum and of energy, by using the principle of minimum of energy. And this statement is very important. Much more important than telling that Greeks invented mechanics first than Turkish, just for pulling the leg of Eden, than Turkish scientists. Okay, by the way, I don't believe there is any difference between Turkish and Greek scientists. Okay, they were the same group. Why this statement is very important? This statement is extremely important because we want to invent new theories. Okay? And I cannot teach you how to invent a new theory, but in one way. I can teach only you how every theory has been invented the first time, so that you have an idea of how every theory has been conceived the first time. Now, this is not my opinion that the principle of minimum of energy is at the basis of everything. I mean, just for using the principle of authority, you have Einstein, Feynman, Landau. Every scholar who did a positive contribution to science actually based his novel models on a set of reasonings following this flowchart. So every model, if you find the original papers of every new model, you discover that they based these models on variational principle. So what I will do now, I will show you how, using a variational principle, Piola and Lagrange invented continuum mechanics. Okay. Why this is important? Because the standard continuum mechanics, which became which became the most used version of it in engineering, needs generalizations. So you will need to not only to learn one theory by heart, but you will need to choose among different possibilities which one is the most suitable for you. Not only, I hope that somebody among you in future will be obliged to learn to invent a new model, something which has not been yet formulated. Okay, and in order to invent a new theory, you must use a variational principle. So all these words now are needed for introducing the total deformation functional. The total deformation functional maps, in order to underline that it is a functional is a map which takes a function and associates to this function a number. Okay, so a functional is defined in the space of configurations and has values in R. Okay, so if I write E tot of key X, somebody may believe that I'm considering the element of E3, one position in the argument of E tot. Okay, instead, the argument of key tot is the function itself. I will give you immediately the correct definition of E tot, like the energy of external forces plus the energy of deformation. And now I give you the expression of the energy of deformation. And this you should understand. W is the local energy of the local density of energy of deformation. So what is behind this definition? This is a definition, remark. You take your C star. You cut your C star in small pieces. Okay? So C star is equal to union on ijk of Cijk. Each of these sets is a part of your body which is small enough that you can write key of X equal key of X0. X0 is the center or a fixed point. So X0, comma, ijk. Okay. Inside each of these C's, you can write key of X like f of x, key of x0 plus f of x0, x minus x0 plus infinitesimals. Okay. Then you say, okay, Cijk is deformed by f of x0. And this we studied in the whole detail. Okay. Okay, look, maybe it is better if we call this with this strange C, because otherwise we can confuse it with the F transpose F. Okay. So, hypothesis. The energy needed for deforming Cijk depends on F calculated in X0 Ijk. Okay? So the total deformation energy will be the sum over Ijk of the deformation energy of Ijk of the cube of the element Cijk, which is a function of F Ijk. So each of these elements is deformed. It is deformed how? By F. This one is deformed by Fijk. I know, remark, that I placed here Ijk. So it means that this here, this material here can be different from this material there. So here I could have aluminum, here I could have iron, or here I could have an alloy of aluminum and another material which has different properties from the alloy in that point. So the same matrix F in different points of my body could produce a different deformation energy. Okay, so I placed, this is the fundamental constitutive equation. It is Wij gives you the mechanical behavior of the subbody Cijk. Okay. So Wij maps Ijk into real numbers. So it is a real number. And it gives you the deformation, the energy, let's say better. It is the energy needed, the energy needed to deform Cijk with, okay, as described by F Ijk. Okay? So this is very reasonable. You did this kind of splitting many times, and this integral, this sum, you agree, becomes integral of Wf capital X. Capital X is reminiscent of this dependence on ijk, d volume x, and this is over c star. Okay. Now, you agree with me, I hope, that the whole function key appears in this formula. Okay. So the function which takes the whole function key and associates to this full function the integral of on C star of W of f of x dvx is a function mapping functions into real numbers. Now, to say this is clumsy. A function which maps functions in the space of configurations and associate to these functions in the space of configurations a real number. This is a very complicated way for telling things, which may be confusing. So mathematicians decided to call functional a function defined in a set of functions having values in real numbers. Okay? So, in order to remember this fact, I wrote this formula with the dot here. I wrote this formula with the dot here because I wanted to underline that the total energy being constituted by a deformation energy plus the energy, the potential of external forces, it must be regarded, it is actually a functional. Okay? And this is the beginning of mathematical difficulties, which start Lagrange on, because we know that for finding the minimum, you need to calculate the derivative. Okay? So if you have a standard function defined in the integral AB having values in R, this minimum here is characterized with mathematical analysis. How? Let us find where its derivative vanishes. This is the rule used for finding minima. Of course, then you find also maxima, and you also find saddle points. So this algorithm has some difficulties in the application, but so that now you can, before we end, I can give you something to go to read in your books for reminding. We must generalize the concept of derivative for functionals. And then we must impose that the derivative of E tot is 0 and find the solutions. Finally, we must distinguish minima. Okay. Now, this program is the basis of a theory which is called functional analysis. Okay, to develop carefully functional analysis as we did for tensor algebra, it is not possible because this is a theory which is very complicated, very difficult. However, Lagrange developed the basic ideas with very simple mathematical tools. So what we will do? We will do the procedure by Lagrange as developed by Piola. So in a sense, while I was presenting to you the tensor algebra of 20th century, so I could explain you, I think, in a relatively simple way, the basic ideas of tensor algebra. I will use the methods by Lagrange for calculating the derivative of the energy functional. So we will not write exactly the formulas used by Piola, because Piola didn't use tensor calculus. Okay, we will use Piola reasoning, writing his formulas using the modern notation of calculus tensor algebra. Okay. So this is the project we have. So this time in this lecture, I did manage to formulate the principle of minimum of energy and to motivate it in the right way. These things should be written in the chapter about naive model, and but we will go ahead in the next lectures. So I think we can stop the video recording.